Hi, everybody. We are back. In the last segment, we talked about the single linear regression model where we had one independent variable on the right-hand side. We had one regressor that we were trying to control for to look at trying to explain the y variable, the regressant on the left-hand side. And we had looked at this in the example or in the context of the La Quinta in location problem where we were trying to predict the operating margin as a function of other variables. And the one variable we had considered last time was the competition variable, which we had measured by looking at the number of competing hotel rooms that were open within a 3-mile radius. What we're going to do today is we are going to look at the multiple regression case where we will actually have multiple x variables on the right-hand side of that equation, multiple regressors, if you will, so that we will be able to predict operating margin based off of a number of other individual features, not just competition, but things like market awareness, various demographic characteristics, different sources of demand, and as well as physical qualities of the location, things like distance to highway or distance from a dump. These would all be things that would affect people's propensity to want to visit a hotel location and hence the potential for us to charge a higher operating margin. So now the model is a little bit more complicated. Okay, we have these different factors that we are interested in here. Right? Competition was the factor, and then we thought about how we would measure that particular factor here. So again, here is our factor, and here is the way we were measuring that factor. So we're going to go ahead and think about now building a slightly more complicated model that has not just one independent variable, but has multiple independent variables. Okay, and the independent variables we're to consider here still are competition variable x1. Okay, but we're going to also add a few other variables. X2 will be the number of miles to the nearest La Quinta Inn, some sort of a market awareness type metric. X3 will be the amount of office space within 1,000, in terms of thousands of square feet in the surrounding community, and the idea being the more office space there is, the more business travelers there might be. We're also going to look at median household income in the surrounding community. The wealthier folks are, the higher we can price them. Again, that'll affect our operating margin. And last but not least, X5 will be college enrollment in the nearby community. The more students there are, the more parents may need to use hotel rooms for those students. And again, that gives us a little bit more market power and pricing higher at our operating margin. So the idea behind the multiple regression here, again, is that there is some population function, and now the population function is a little bit more complicated. Okay, we still have our usual vertical intercept term here as beta 0. But now, because we have multiple factors, multiple inputs, or multiple regressors on the right-hand side, we have multiple population parameters that we have to capture that measures the slope with respect to these independent variables. Okay, so that's really the big difference here. And we still have our error term, epsilon, that noise term, and we're trying to predict, again, our operating margin here on the left from these different variables. Competition was the first variable we started looking at when we were modeling this in the single variable case. But now we've added a few other variables to the mix here. We have things like market awareness, enrollment in university. So if you wanted to think about writing out the regression equation for the population function here, without actually plugging in the values for the betas, because we don't know those, right? We're going to have to take our sample data and estimate those betas with our lowercase b estimates. The model is going to look something like this. Okay, so this is what we want to be able to estimate. We want to estimate this, so we want to figure out, again, all of these different coefficients, all these different parameters that would describe each of these different effects. Okay, so that is the goal. Now, if we had only 2 x variables, okay, so for a minute, we're going to abstract away from model 2 here. We're going to look at just a case conceptually of 2 x variables. Well, remember, with 1 x variable, we kind of had a 2-dimensional picture. We had y on the vertical axis, we had x on the horizontal axis. But if we have 2 x variables, our regression model is no longer a line in 2 dimensions, but it is actually a plane. And general name for regression. It is a type of what's known as response surface model. In a sense, we are estimating here a surface in 3 dimensions or potentially hyperdimensional space, and that surface allows us to capture how the response variable y functions with the control variables, our regressors, the x variables here. So in this case, what we're looking at here is a 3-dimensional plane where in one direction we can look at the slope with perspective, or with respect rather, to changes in the x variable, holding the x2 variable fixed, right? We're looking at the changes in x1. But we could also think about taking a slice of this picture along the y-x2 plane here and measuring the slope for the x2 variable holding x1 fixed. Okay, so a little bit more complicated. We have multiple slopes we have to worry about now, and that's what B1 and B2 will tell us from our data. So let's go ahead and look at a mock-up here if we had some data points to think about. So in this plane x1 and x2, we can think about plugging in a particular x values observation. Okay, and suppose the actual y value associated with that observation is above the plane. Okay, meaning our regression plane is going to underpredict this observation a little bit. Okay, so that is our sample observation. Okay, what is the y value? Well, it is up here on that y-axis. And again, here is our regression equation. And if we wanted to find the fitted value, right, what was the fitted value? Well, the fitted value was this thing we were calling y hat. Then the way we would do that is by essentially taking that data point that we've drawn down here, and we're going to project that straight up into the plane, and we'll see that data point hits that plane right there. Okay, and again, along the vertical axis, right, here was yi, here is y hat. So we can see the distance between those two things is the residual associated with that particular data point, just like we saw in the 2-dimensional case. But this is a higher dimensional case. We have an extra x variable here. Okay, so again, the calculus problem that we're solving now is a little bit more complicated. We have to minimize the sum of the squared residuals, not just by choosing beta 0, b0, and b1, but we have now a third parameter to deal with, right? We have 1, 2, 3 b values that we would need to estimate in order to describe the model drawn in this 3-dimensional diagram. Now, what we're going to do is we're going to jump back to our model 2. Okay, and again, model 2 involved us estimating a situation where we actually had 5 independent variables on the right-hand side. So our model 2, we're not going to be able to draw in 3-dimensional space because we have 5 independent variables. So we would actually need a 6-dimensional space to draw that picture, and we can't really do that here. So what I would like to show you next, and this is going to be a very important part of our application for what we are doing in our course, is to be able to interpret the output that the computer would provide you if it ran the statistical analysis of solving this calculus problem that is, or rather that involves, minimizing the sum of the squared residuals. So the output I'm going to show you here is from the Excel regression analysis package. So it's fairly simple to implement this. I'm not going to show you that in this video. I will follow up with another video to show you how to implement regression using a computing package. But there's a lot of output to take in here. And I want to spend just a little bit of time discussing some of the elements of the output here. So let's go ahead and highlight a few important values. So the first thing that we would like to know here are our coefficient estimates. Okay, so these values in this first column, these are the b values associated with each one of the individual variables. Again, for example, this coefficient right here, negative 0.008, we saw that before. That is the coefficient on the competition variable. And you might say, oh, that's weird. That was the same value as it was in the single linear regression model, in model 1 that we looked at in the previous segment. that generally will not happen. If you add more variables, it will wind up changing the B parameters on other variables that were included in the regression. So this is a little unrealistic in this example in that regard, but we're going to roll with it. This coefficient here represents B2, which is the coefficient or the parameter multiplied by our awareness variable, so on and so forth. So these coefficients here, this is really the most important thing to see if you wanted to write down the structure of the regression equation itself. Okay, so if that's the goal, let's write down the regression equation. This is the column I would need to do that. That tells me all the different B's. Okay, there are a couple other metrics that we're going to spend some time talking about momentarily. The R-squared metrics are important up here. These will tell us actually about how good the model fits the data. And of course, we also have some values related to hypothesis tests over here. We actually have a T-statistic, and we're going to talk about this in a minute, and the associated p-value for that T-statistic that runs what's called a significance check on each of the individual effects, on each of these individual X variables to see if the effect of that variable is statistically significant in being able to predict or explain the operating margin. Okay, so we're going to go ahead and talk about these values in a moment. We'll discuss the output of this ANOVA table, which stands for analysis of variance, momentarily. But again, for now, if I want to describe that regression model, it's really this first highlighted column of coefficients that we would need to do this. Okay, so moving forward, what we've done now is we are in a position to write out the estimated equation here for the regression surface, for that hyperdimensional surface, where again, the left side is the predicted value of Y, B0 is our intercept term, and all of the other B's that are not B0 are our estimated what we call slope coefficients for that hyperdimensional surface. And if we plug in the values in that first column into this equation, we will see the equation for the regression model, which looks like this. Okay, now we've not really assessed the model yet, but at first pass, we can kind of look carefully at these coefficients, and it's going to suggest the following. Okay, you'll notice some variables have positive values in front of them. Okay, meaning there's a positive relationship between that variable and the operating margin on the left-hand side of the equation. But there are other variables that have a negative sign in front of the variable name, right? They have a negative beta value or a negative B value. And the values with positive B values, these are ones that will be, again, positively associated with Y, holding changes in everything else fixed. And we can see here which variables those are, right? If we have any increases in, let's say, let me use a green arrow here, but if we have any increases in things like market awareness, right, which is the distance to the nearest La Quinta, the amount of office space, the college enrollment, as well as the median income, all of those metrics there are associated with positive coefficient values. You can see there's a plus in front of those things, right? Because of that, we know increases in those things will push operating margins up, and decreases in those features will push operating margins down. Now, you'll notice there is one factor here, and it's a familiar one. We saw this before, that is negatively associated with the operating margin, and that is the quantity of competition. Is the quantity of competition. And we can see that here because the coefficient in front of competition is a negative number, negative 0.008. And that suggests that increases in the number of nearby competing rooms will negatively impact the operating margin. That is what this model is predicting here. So the signs of those coefficients are super important. They're related to the correlations. They're related to the covariance of those individual variables with the margin itself. Okay, but the other thing they'll let us do is quantify the degree of one of these effects. Okay, so we can plug in a counterfactual value for each of these variables, for each of these x variables, and we can use the model to predict what will the resulting operating margin be by computing the fitted values, just like we had done in the single variable case. Now let's talk a little bit about assessing the fit of the regression model. Okay, we're going to look at 3 different metrics that are related to variation in our model. The first metric is something known as the SST metric, okay, which measures the total variation in y around its mean. And this is going to look a lot like the variance when we take a look at the SST metric in a moment. But the SST metric can be broken down, and this stands for sum of total squares, or sum of squares in total. It can be decomposed into 2 components. So we have, again, the sum of squares total on the left. And if you look at the way we calculate this thing, okay, this looks a lot like the variance of y. In fact, if we divided it by, n, or a degree of freedom adjustment, n-1 or n-k in the case of a regression, we could interpret that as a variance metric, right? We're measuring the square deviations of y from y bar. So if we divided it by the number of observations, that would look a lot like the population variance for y. Okay, the sum of squared errors. Okay, this is the sum of squared residuals, which was the function that we tried to minimize, right? Or rather, the computer did the dirty work for us in finding or calibrating those optimal b values. Okay, so this value inside of here, that is just the residual squared, right? Note there's a little bit of difference between SSE and SST in that SST measures how far a data point is from the mean value, but SSE measures how far the y data point is from its predicted value. And the predicted value, it's a type of mean called the conditional mean, right? Like conditional probability. It's the mean, but conditioning on the particular x values. Y bar is the unconditional mean, right? Regardless of the x values, just the average of y in the data. Okay, this last term, SSR on the right, is the sum of squares for the regression. And this measures something a little bit different. And what the sum of squares of the regression, or SSR, actually measures here is really the deviation, okay, in the predicted value relative to the mean value. Okay, and again, y hat is the conditional mean, y bar is the unconditional mean. So we're looking at the squared deviations between the predicted value and the average value in the data set here. Okay, now, in terms of measuring variation in our model, right? And that's really what we're trying to do is we have these x variables that are fluctuating. And we want to know how much do variations in those x variables explain variations in the y variable across observations. So SST, again, this is our total sum of squares. It measures the variation of the observed y values around the mean. SSR is the explained variation attributed to the relationship between x and y, right? We're measuring y hat relative to y bar. And SSE, this was our sum of square residuals. And this is variation attributed to factors other than the relationship between x and y. Remember what the residuals were. They contained the unexplained information that we didn't include as independent variables in the regression. So if the regression is a good fit, meaning we've incorporated a lot of information that relates the x variables to the y variables, the sum of the squared errors is going to be relatively small compared to the total sum of errors. And if we had a perfectly fitting regression line that went through every single data point, then SSE would be equal to 0. And the magnitude of SSE depends on the number of observations as well as the units of measurement of the output variable here. And I'm going to use this diagram again in 2 dimensions just to kind of help you think about these components here. So this diagram is a little bit of an abuse of notation, but let's suppose we have this observation. So we can see here the actual y value. We can see the predicted y value from the regression line. But suppose that the average value of y in the data set is much lower than Okay, so we don't have the individual data points here, but let's suppose the actual average value of y is here. Okay, then we can think about, for just this one data point, what the SST measurement would entail, right? That's the difference between y and y bar. We're going to measure that deviation. We're going to square it. And then we would add that up across every single data point here. So this summation, and we wouldn't really sum on just one data point, but we would sum over all of the other data points if I had a bunch of other green dots drawn in this picture. Now, the sum of the square residual, what is that? Or the sum of the regression squares, that is the difference between y hat and y bar. Okay, and again, we would square that, add it up across every data point to calculate the total SSR. And the SSE metric related to this particular data point is the difference between the y value and the predicted value here. So I think this is a nice diagram, and you can see definitely how the breakdown of SST is related to SSR and SSE. Now, I would like to jump back to our model to output in Excel, and I want to reference where you can find these values here. Okay, so SSR, that purple value, that shows up right in this first line of the ANOVA table. So that was this big table here in the middle. Okay, that tells us the decomposition of our variability, of the variance. It's the analysis of variance. So here is our SSR, here is our SSE, and here is our SST. And you should be able to verify with those values, provided that this relationship definitely holds true in the data. Okay, now, if we were given some different information, like let's suppose we had a different regression that we ran, and here is the output that Excel gives us. So here is our ANOVA table. Okay, and you'll notice it's asking us here to find out what is the SSE term. So all we would have to do to find SSE is we would take SST, we would subtract SSR, and if we did that, we would find SSE is 10.44. That is the sum of squared residuals in this problem. Now, these values here, SSR, SSE, and SST, they are important because they're related to the coefficient of determination, which is also known as R-squared, the R-squared of a regression. And the R-squared of a regression measures the degree of fit in the data relative to our model. Okay, so it's asking, or really, how well does the model fit the data? Okay, and again, this is a measure of relative fit based on a comparison of SSR, SST, and SSE. You can actually compare all three. And it reports the total variation in Y that is explained by the variation in all of the X variables jointly. And the way we calculate this thing is by doing 1 minus SSE over SST. And remember, if we had a perfectly fitting regression line, like if our regression line fell right on top of every data point, SSE would be 0, meaning a perfect fit would give us an R-squared of 1. You can also show with a little bit of algebra here, if you changed 1 and you got a common denominator, SST over SST, you can rewrite the R-squared metric as the ratio of the sum of squared in the regression to the sum of squared total errors here. And again, the nice feature of R-squared is it's between 0 and 1. The lower R-squared is, the less of a fit we have to the data using our regression model. Okay, meaning that our X variables don't really explain the Y variable at all. The closer R-squared is to 1, okay, the better the fit of the model is. Okay, if we have an R-squared of 1, that means 100% of the variation in Y is explained by variation in the X variables here. Okay, so if we had to calculate the R-squared given the information in the table, okay, so let's go to this example again. We looked at this example earlier, and there's a couple ways you could write it, right? We know SSE is 10.44, so you could do either way here. But I think it's easier to just use SSR, which was given to us already, right? SSR is here. SST is there. So if we calculate the ratio of SSR to SST, that gives us an R squared of 0.6485, which means the particular regression model that generated this statistical output, the X variables in that model explain 64.85% of the reason why the Y variable fluctuates between data points, from data point to data point. Okay, meaning if it's explaining about 65% of the variation in Y, it leaves unexplained about 35% of the variation. So 35% of the reason why Y fluctuates is not explained by the model, which means there are other variables that we may want to consider adding to the model to capture that unexplained information. So in terms of some cosmetics here with our regression diagram, which of the figures show that none of the variation in Y is explained by the variation in X? Well, you'll note in figure 5 here, the X variable can change, but the regression line predicts Y is going to remain the same, meaning X can change, but it does not cause Y to fluctuate. So figure 5 is the culprit here. Okay, in figure 1, okay, there is a positive relationship between X and Y, but there's a lot of dispersion. So we have an R squared there of about 0.6. You'll notice figure 2, we have a stronger but negative relationship. So the R squared in figure 2 is a little bit higher than the R squared in figure 1. Okay, that line fits that data a little bit better. In figure 3, we have the strongest possible negative relationship. We actually have a perfectly correlated Y and X variable, but they're negatively correlated. And in that instance, the R squared is equal to 1 exactly. That regression line perfectly fits every data point. Similarly for figure 4. Okay, it's a positive relationship, but that regression line perfectly fits the data. And in the last figure, we had an R squared of 0. Okay, so note that we can come back to our regression output here, and we can take a look now at that R squared, which was equal to SSR over SST, or 1 minus SSE over SST. So we can check that that is indeed the case here. And the way to interpret this is that the X variables in our model, what are those? Well, they were competition, awareness, office space, income, and enrollment. Okay, those X variables are capable of explaining 51.69% of the reason why we see variation in the operating margin between observations. Okay, those X variables in the model are capable of explaining around 52% of the variation in the Y variable, which means at the same point we've left unexplained about 48% of why the operating margin tends to change between observations. Now, the other thing I would like to take a moment to do here is I want to talk a little bit about the portion of the table output here that is involved with hypothesis testing. There's actually 2 portions. Here's one, here is another. We'll come back to the F-test in the next video segment. But I want to go ahead and talk specifically about testing whether or not individual variables in the model have a statistically significant effect on the Y variable in our regression. Now, if you look at our coefficient estimates, I think there are a couple values that you would need to be a little skeptical of here. Note the competition coefficient is very close to 0, 0.008. That's pretty close to 0. Okay, and it also looks like here our office space value is pretty close to 0. Okay, and we know that if we had sampled a different set of observations, if we sampled a different 100 La Quinta-ins to generate these coefficient estimates, there would be some sample error, some sample noise, and those coefficients would change a little bit, and that's actually reflected in this column here that measures the standard error of each of these coefficients, and we'll talk about that a little bit more again in the future segment. But my point is the following. Just because the model tells us, hey, we had what looks like a negative 0.008 effect from competition on the margin, it could be that that really small value in magnitude is just from sample error, and maybe that value is 0. Maybe competition actually does not affect the operating margin, and we can make the same argument potentially for office space here. So again, the question is now, if we have some B parameter that is really close to 0, how far away would it need to be in order for us to say that that variable is a significant component of our model? And again, the way we think about in statistics, how far is far enough away from a hypothesized value? Well, we're going to run a two-tailed hypothesis test here. Okay, we're going to assume as the null hypothesis that the variable is insignificant, meaning this hypothesized value of beta that we're looking at here, okay, is sufficiently close to 0. So we're going to assume under the null that that value is 0. And then we're going to test that against the alternative that as long as the value is farther enough away in either direction, positive or negative direction, okay, that will provide enough statistical evidence that we should include that variable in our model because it does have a statistically significant relationship when trying to predict the y variable, which is the operating margin in our case here. So let's go ahead and talk a little bit about the t-test again. This is something that's not new here. But we're going to use the t-test to check the statistical significance of the individual B parameters. And you could do this for the intercept and the slope terms. And what this does is it shows if there is a statistically significant linear relationship between a particular value or variable xi and the y variable we are trying to predict. So the null hypothesis is going to be, we're assuming here that there is no relationship. Okay, so we're going to assume that the actual B value is 0, and we're going to try to look for evidence against that. Okay, so you'll note the form of the hypothesis structure here suggests we're going to be using a two-tailed t-test. Okay, and again, the way we're going to do that here is we're going to calculate our t statistic. Okay, so this looks very similar. This is like x minus mu over sigma to some extent here, except the value we're going to be substituting in for beta I there is going to be 0. So this value here is going to be 0. So the way we're going to calculate this t statistic is pretty simple. We're going to take the B value that we estimate, we're going to divide it by the denominator here, which is the standard error of the slope estimate. Okay, it's the standard deviation of the slope estimate itself. And remember, the slope estimate, right, that's a particular parameter estimator. It's a slope estimator, and we know there is sampling noise there. If we sampled a different set of observations, those slopes would change a little bit. And that is what SB is measuring down here. And again, we'll talk about how to calculate that in a later segment. But let's look at some output from that Excel table here. Let's specifically look at the output associated with the competition variable, since we recognized the competition variable had a very, very small partial effect. It was negative, but it was small. And the question is it far enough away from 0 in the negative direction for us to reject the null hypothesis in favor of the alternative that competition does have a statistically significant effect on the operating margin? So let's go ahead and we're going to run this test here. You'll note we're doing this at the 5% level of significance, which is pretty standard, but you could use 10, you could use 1. Those are all three really standard levels of significance that are used. But here is the question, right? Is B1 actually a significant feature in our model? Yeah, that's what we want to be able to answer here. And we're given the standard error in the output. So if we were to take B1 and divide it by that standard error, you would wind up with this t statistic on the right-hand column. Okay, so that t statistic, negative 6.1676, that says that that observation there, that sample statistic, is more than 6 standard errors below the mean of the distribution, which probably sounds pretty far away, but we're going to check this. Now, the other thing we know is with the t-test, we have to use the degrees of freedom to calculate our critical value threshold. And you'll notice here the degrees of freedom looks a little bit different than it did when we were doing this for the sample mean. Okay, and I want to just take a moment and explain why that's the case. Okay, it turns out the degrees of freedom here, and in general for any type of model, are related to the number of parameters that you have to estimate. So I'm going to argue here that the number of parameters we had to estimate in this model are k plus 1. We had k variables, but we had one intercept term. So you could equivalently think of the degrees of freedom as n, the number of observations, minus the quantity k plus 1. Okay, so what is n? N is the sample size. Okay, and that value here, k plus 1, what is that? That is the number of parameters that we have to estimate. Okay, now when we were dealing with the sample mean, how many parameters did we estimate with the sample mean? It was just one, right? The sample mean, x bar, that was the one parameter. Okay, so the degrees of freedom adjustment in that case was n minus 1. But now our degrees of freedom is going to be n minus the number of B's we have to estimate in our model. So the more complex the model is, the more B's we need to estimate, the more variables we have on the right-hand side, the fewer degrees of freedom we will have when we compute the T statistic here. So if you were to go to your T table, okay, and since we're using a 5% level of significance here with a two-tailed test, you should be able to go to your T table and you can plug in here 94 degrees of freedom, and that corresponds to a value, a critical value threshold of 1.985 on either side. Meaning our rejection region here, we can see in this diagram. Okay, so all we're looking for is evidence that that sample statistic generated from our coefficient estimate is farther away than 1.985 standard errors under that sampling distribution. And you'll note the T value for the competition coefficient is way farther to the left than that threshold, meaning we can reject that null hypothesis here. Okay, we can reject that null hypothesis. So the conclusion here is that there is sufficient statistical evidence that the number of nearby competing rooms does affect La Quinta's operating margin. All right, now let's go ahead and take a look at the T statistics for all of these variables, for all the B's that we had looked at here. So in this diagram, okay, I've just pulled that particular column where we have the T statistics over here for all of the B's we've estimated for the intercept and all of the slopes. And the question is, which of the following statements is correct? And we have our critical value threshold here. Given that we're using a 5% level of significance, we have 5 variables and we had 100 observations. And the question is, given our critical value threshold, okay, which variables are significant and which ones are not? So any variable with a T statistic larger in magnitude than 1.985 will be significant at the 5% level. So note, the intercept is significant, competition is significant, the awareness variable is significant, office space is significant, despite the fact that we said its value is really, really low. It's actually significant. It is far enough away from 0. Okay, income is significant, but we have an odd man out here, and the odd man out is the very last variable, which is college enrollment. College enrollment doesn't quite pass the muster in terms of being far enough away from 0 to actually be statistically significant. Okay, now you'll note the only answer choice here consistent with that is choice A. We would reject the null hypothesis B3 equals 0. Okay, but we would not fail to reject the null hypothesis B4 equals 0. We said that is significant. C is wrong because not all of the independent variables are individually significant. Right? The last one is not, enrollment is not, and D is also incorrect here. So the interpretation here, with respect to specifically that null hypothesis in A, is that there is evidence that the available office space in the area does affect La Quinta's operating margin. There is statistically significant evidence there that that is the case. Now, what I would like to talk about next are related to the standard error column here of these slope coefficients, of the coefficients in this first column. So let's go ahead and talk a little bit about the error in those slope coefficients in that first column, which are measured by the standard error in the second column, which tells us in some sense the reliability of these slope coefficients. So before we get there, I want to just talk a little bit about a general rule of thumb. Okay, and this is kind of a quick and dirty calculation here, but you'll notice that the critical value threshold was around 2 in this example. Okay, that corresponded to an alpha of 5%, but we had some degree of freedom adjustment related to N and K here. So a general rule of thumb that you could apply, for example, if your statistical output is somewhat limited and you can't really see the p-values, but a general rule of thumb here is that if the t-statistic is larger than 2 in magnitude, then you probably have a statistically significant effect there. Right? You can be confident that the estimated regression coefficient is not just random from your sampling error. It is statistically significant. And this quick and dirty method should only really be used if the standard error or the p-value are unavailable or can't be calculated with the given information. And fortunately for us, our statistical output will report the associated p-values for this test. So it's important to realize that the p-value approach is actually much easier to implement here. Because rather than having to know a particular level of significance, if we know what the p-value is, then our decision rule is fairly easy. Okay, if the level of significance is 5%, then we're going to be able to reject the null hypothesis if the p-value that the statistical output reports to us is less than that value of 5%. Okay, so again, remember, we're looking for very small p-values to be able to reject the null hypothesis. So the smaller the p-value, the stronger the evidence of rejection. And we can go ahead and look at this example here. And we're going to look at this last column. And I want you to note at the 5% level of significance, we can see immediately, without needing to compute the t-statistic, without even needing that standard error column, we can see immediately which variables are significant at the 5% level because they have p-values that are smaller than 0.05. So the intercept is significant. Competition is significant. Awareness is definitely significant. Office space is significant. Income is significant. But as we saw before using the critical value approach, enrollment is not significant. The p-value there is 14.4%, which exceeds the p-value, or rather the level of significance of 5% of the test. So in this case, if you look carefully at your answer choices here, choice B is correct. We would fail to reject the null hypothesis that B5 equals 0 based on that p-value. All right. Let's go ahead and take a look at another question. Okay, again, so given this information, okay, which of the following statements is correct here? And again, we have our p-values in this column that we want to look at to be able to think about this. Okay, so if you want to pause it and take a moment, that's great. But what you should see here is the conclusion is there is not enough statistical evidence to conclude that college enrollment affects La Quinta's operating margin at the 5% level of significance. And what that would tell us to do is maybe re-estimate the model, but drop variable number 5. Don't include enrollment there. It wasn't significant. Okay, and that may improve our predictive power here. Now, we're going to start talking about model selection in the next video segment. So we're going to wrap up here and we're going to pick up discussing the effects of adding more variables into the regression and how we can compare the efficacy of different regression models and trying to capture the best relationship between the X variables and the Y variable. What is the best model? Okay, what are the right X variables to include to give us the best prediction of the Y variable? So hope you enjoyed that. We'll see you soon. And good luck.